margin around the edge, which you almost certainly won't see. But it's good to make it a little bigger than it used to be, because I've made several videotapes where after it's all said and done, and you take the tape and put it in a different VCR.
What is four-dimensional space? How can we visualize it? And what is there to see that is mathematically interesting and useful? These are our topics. Understanding four dimensions begins with a close look at three dimensions. A knotted circle is an excellent tool for the mathematical investigation of three-dimensional space. It is a non-intersecting placement of a circle in space. Two placements are equivalent if we can flexibly move from one to the other, allowing no self-crossings. Generally, such a motion is called a deformation or isotopy. A circle is a one-dimensional object, and we adopt a topological viewpoint. So we should depict a circle graphically as a thin and flexible object. But to make it easier to see, we will often thicken it or portray it in rigid form. A circle is knotted if it cannot be deformed into the plane. A knot captures the essence of three dimensions in spite of its intrinsic one-dimensional nature. Analogously, there are knotted surfaces in four-dimensional space, those that cannot be deformed into three-dimensional space. They similarly capture the essence of four-dimensionality. The surfaces we consider are the sphere and the torus, here shown as subsets of three-dimensional space. If we spin a semicircle in space with the endpoints fixed, we generate a sphere. A torus can be obtained by taking a circle and spinning it in space. The knottings we will look at will take advantage of this. The images that we see in three-dimensional space are going to be taken to be the standard unknotted sphere and the standard unknotted torus. When we see a knot in space, we really see the projection of it in a two-dimensional field of view. This planar curve is called the projection of the knot. This projection is missing some information, the value of the projected coordinate. We can encode this information by the use of color. Blue points are high and green points are low. Think of blue sky above green grass. Sometimes we use a red-blue color gradient. Once we have encoded the knot, we can topologically reconstruct it from the color-coded projection. Visualization of knotted circles does not require such color coding. However, we will see the utility of an analogous coding in the projection of a knotted surface. In four-dimensional space, we obtain a knotted torus by spinning a knotted circle, here shown in projection. This surface does not intersect itself in four-dimensional space. To see how we make this, think of spinning the projection of the knot in three-dimensional space. We sweep out a two-dimensional set. The union of the spun projections fills up the projection of the spinning. That is to say, the spinning of the projection is the projection of the spinning. One cannot do this construction in three-dimensional space by taking copies of the knot, for this would result in genuine self-intersections of the surface. Consider the torus in three-dimensional space. We fill space with half-planes all having a common line. Place a circle in each half-plane and we obtain the standard torus. The projection of the knot in the half-plane we have shown is really the projection of a non-intersecting circle in a copy of half-space. This is the key to understanding the projections of our four-dimensional surfaces. Four-dimensional space may be filled with copies of half-space in such a way that each projects to a half-plane such as we have seen. These half-spaces are disjoint except for a common plane indicated in red. By placing a knotted circle in each half-space, we obtain our knotted torus in four-dimensional space. Here is a projection of a torus in four-space, using a red-blue color gradient for the projected fourth coordinate. By the variety of colors, we see that it does not lie in three-dimensional space. This projection, however, is a subset of three-dimensional space and as such is knotted in three-dimensional space. We rotate this object rigidly in four-dimensional space. At the end, the image is clearly unknotted. The projection, a subset of three space, is equivalent to the four-dimensional object by a deformation that alters only the fourth coordinate of the point. Putting these deformations together, we see that the knotted torus in three space is unknotted in four space. A variation of this argument shows that any knotted circle in four space is unknotted. We are now viewing two full rotations of this object in four-dimensional space. So far, all rotations we have used have been in three-dimensional space as we have rotated the projection of a knotted surface. Now we are considering rotation in four-dimensional space. As we rotate near points where the projection appears to intersect itself, the parts of the surface are of different colors. This demonstrates that there is an actual separation in four-dimensional space. In three-space, we consider another placement of the torus. Topologically, the circle and the square are the same since we can deform one to the other. We augment our spinning by incorporating this deformation. The beginning and the end of this deformation agree, giving us a nice surface with no unmatched edges. We rotate and use a clipping plane to cut away portions which are closer or further than a certain distance. Thus we can see in a dynamic way the deformation which gave rise to the object. Using symmetries of a knot, one may define a deformation we call turning. We may use this, in turn, to define many knotted tori, depending on the amount of rotation. We might consider, for example, a complete rotation of one full turn. Another possibility is to use a fraction. For example, this next one shows a 1/3 turn. We move these surfaces in four-space by rotational deformation and view the details of the projection by moving clipping planes. Using front and back clipping planes, we get two copies of the knot we are using as well as the turning motion. We look at the results of a 1/3 turn, a 2/3 turn, and a 2 turn. It might seem like we are looking at an infinite supply of knots, but in fact there are only three distinct possibilities. The torus with 0 turns and the one with 1 turn are different, as shown independently by Livingston and Boyle. The example with 2 turns is equivalent to 0 turns, using some basic facts about the space of rotations in three-space. It is somewhat of a surprise that the example with 1/3 turn is unknotted. Slice away the points with the last coordinate greater than 0, then eliminate points with last coordinate less than 0. What remains is the projection of two unlinked and unknotted circles. One slice is not enough. We need more information. We reassemble the projection and look at a particular deformation of this torus in four-dimensional space. Of course, we really view the projection of this deformation. For reference, we put a knot in the center of the graphic. In this deformation, the projected points of the torus go through the hole where the knot is, rather than around the hole in our previous graphics. These two possible motions, which in the projection seem to go around the hole or through the hole, are different yet closely related. The torus is a product of circles. In the motion, we see the deformation corresponds to a rotation in one factor and not the other. In our first look at this example, the roles of these factors were reversed. If we slice the projection at any time as shown, we get a similar picture. The blue plane we see is the projection of a three-dimensional space, and the two-dimensional curves are non-intersecting subsets of that three-dimensional space. In particular, the apparently concentric relation of these circles is not significant, for in fact we have two non-planar curves in space. We see two curves that perform a turning motion. This should remind us of the first pictures of the motion of a 1/3 turn torus, where we use clipping planes, saw two copies of the knots we were turning, and also dynamically saw this turning motion. This is exactly what we are seeing. We are seeing that the 1/3 turn trefoil torus is exactly the same as a 3-turn trivial knot. It is easy to see that the latter is unknotted. Thus, the 1/3 turn trefoil knot is unknotted. The same analysis can be extended to find other relations among the family of turned knotted tori. We now look at some knotted spheres. Take an arc with a knot in the middle as shown, and spin this about, keeping the endpoints fixed. This gives rise to a knotted sphere. This knot was defined and studied by Émile Artin in 1925. We examine the projection of this knot by taking successively further clipping planes. We next use successive clipped slices. What we see is the projection of part of the knotted sphere which lies between two parallel hyperplanes in four-dimensional space. We do this more slowly now. The first slice we have is a pair of discs, then we get two annuli. These then join to give a disc with two holes, and finally in the center we have a single annulus, which is a knotted band. Note in each slice we have useful color information. If we slice the knotted sphere we have been viewing by a single hyperplane as shown, we will obtain a single knotted circle. The view we see here is of a planar self-intersecting curve, but this is an artifact of our projection. Knotted circles obtained this way are called slice knots. It is known that not all knots are slice knots. For example, a single trefoil knot cannot be a slice knot. We now show a rocking rotation of 90 degrees in four-dimensional space to give us a better view of this slice. Next, we use a three-dimensional rotation to get a better look at this knot, and we can see that this is a square knot. That is, it's obtained by a right hand and a left hand trefoil tied on the same circle. We next take our spun knot and apply a four-dimensional rotation of 90 degrees. At the end of our rotation, the projection of the knot is a flattened, self-intersecting disc called a ribbon. This disc, viewed edged on, may be derived from the projection of our original knotted arc. A knotted two-sphere obtained in this way is called a woven knot. A theorem says that all spun knots are woven knots. Our computer graphics have shown us an example of this and in fact given us the essence of that general proof. An important generalization of the spinning construction is twist spinning. We generate deformations of a knotted arc by allowing the knot to twist as we spin it, keeping the endpoints of the arc fixed. We can give any one of a number of twists as we go around. We show here the result of two full twists. This is a particularly interesting knot since it is the simplest one that exhibits certain complex behavior. By clipping away half the projection as we rotate, we can dynamically view the twisting motion. Also, by adding a tilt to the projection, we can see other slicing views of this object. One thing to note in this projection are the triple points where, in the projection, 3 points of the sphere are mapped to 1. It can be shown that any projection of any deformed image of this knot must have such triple points. Such knots present considerable mathematical challenge. Knots without such triple points are much easier to classify. Now we take this knotted sphere and perform two deformations. Each of these deformations is obtained by a four-dimensional rotation through an angle of 90 degrees. Since these particular deformations are in fact rigid motions in four-dimensional space, it is important to keep in mind that the apparent changes in shape we observe are changes in the projection and not in the object itself. We have now seen several knotted surfaces. How natural are these placements? For circles in three-space, one mathematical answer to this kind of question lies in the idea of the energy of a knot, first considered by Fukuhara. The knotted circles and arcs we have used are all at locally minimal energy with respect to some energy function. Here is a knotted sphere that has been produced by a discrete approximation of such a surface energy. The initial placement was the two-twist trefoil, which we have just seen. This knot has not yet achieved a stable energy configuration after many months of intensive calculation. We are using here a program evolver of Ken Bracke. Note as we turn how the light reflects from the facets as we rotate. This can be used to detect subtle changes in the evolution motion. We would be remiss if we did not mention one more example, the one-twist spun trefoil knot. Although this looks very similar to the two-twist example, there is a big difference This sphere, in fact, is unknotted. This was proven by Roseman, who defined and first studied these knots. This is yet another example of a knot obtained by spinning a non-trivial knot where the resulting surface is unknotted. Any deformation of a knotted circle which returns to its original position can be used to generate a torus in four-dimensional space. We show a knot which is a composite of two copies of the same knot. At the end of the deformation, the first and second knot appear to have changed places, and the initial and final position of the curve is the same. A subtle but important aspect is the manner in which the smaller knot travels around the larger one. It has the freedom to twist as it travels, thus incorporating all the complexities of the twist-spinning construction. Here is the knotted torus that we obtain. We call this a deform-spun torus. This general construction was first introduced and named by R.H. Fox. We can describe this example in a different way, beginning with a trefoil and moving it like a wave across the surface. This construction is called spinning a knot along the projection of a knot. We examine this with clipping planes as before. In general, knots are not given by formulas or equations. For twist or turn spun examples we have seen, one can begin with coordinates for a single knotted circle or arc and use this to generate the data for the knotted surface by means of formulas. These deform spun examples, however, must be constructed by more complex means. There are no simple formulas to describe the deformation we begin with. Because of this, the generation of the surface data from the deformation is not a straightforward matter either. In this next example, we have two different knots. This time we will show an example of a knotting of a sphere. Since these knots are distinct, we must use a more complex deformation in order that the original position is regained. We may think about this deformation as a dance of knots, which, as in an old-time square dance, all dancers return to their original positions. Here then is the knotted sphere we obtain by the deformation we have seen. We will examine it in the same way that we have examined some of our other knotted surfaces. As complex as this may seem, it is still one of the simpler kinds of surfaces that can be obtained by this construction. These are really just first steps at examining these kinds of knotted surfaces. One would like to use the tools of energy functions and higher kinds of deformations to get further looks at what these surfaces really are and to discover the relationships between the various classes of knotted surfaces that we can obtain by these methods. We take one final look at our deform-spun knotted sphere. Here again, we take a rotation in four-dimensional space by an angle of 90 degrees. That which we visualize most easily are surfaces. Four-dimensional space presents a challenge to mathematical visualization. So we bring our best visual tools to the most challenging visual problem, which at the same time is of considerable mathematical interest. We have now seen some visualization tools. We have used these tools to view some objects in four-dimensional space. And most importantly, we have been able to see the use of these tools to find mathematical relationships between some of these objects. The key to understanding the mathematics of four-dimensional space is an understanding of the associated mathematical objects and problems in three-dimensional space. We study knotted surfaces in four-dimensional space. In 3 dimensions, knot theory focuses on circles. Placements are equivalent if there is a motion in space that takes one to the other. In geometry, motions are rigid. In topology, we allow flexible motions called isotopies. A round circle is called a trivial knot. This final circle is tilted in view, making it look elliptical. We view this later from a second viewpoint. Presented with a knotting, we might ask, is it equivalent to a trivial knot? If so, there is an isotopy to a round circle called an unraveling. This unraveling has been produced mathematically using knot energy. Think of the knot as composed of points which repel each other so that the closer points are to each other, the stronger the repulsion. The totality of the self-repulsion is a number called energy. We allow the knot to move so that it will always reduce this energy. One expects this reduced energy configuration will be somehow simpler than the original. Spheres knot in 4 dimensions, much as circles knot in 3 dimensions. We see the image of this object from 4 space projected to 3 space. That is, we display only the first 3 coordinates of points. As with circles in 3 space, it